Okay, so today I'll talk about causality constraint in CFTs in d greater than 2. So the outline of the talk is following. First, I'll talk about crossing symmetry in conformal field theories. Then I'll introduce shockwave states. So today the goal is to study commutators in shockwave states of CFTs. And I'll show that there might be some problems if you consider shockwave states. That will lead us to 4-point functions and what constraint that causality or what's the causality condition that you can impose on a 4-point function. And finally, I'll talk about constraints. So the goal of today's talk is basically first to show that in a CFT, in Lorentzian signature, the causality is guaranteed by reflection positivity and crossing symmetry. And then I'll derive some constraint using that fact. Before I proceed, let me just give you a brief summary of last lecture. So let me draw the diagram that. So if I start with a Euclidean correlator and perform an analytic continuation, if I don't cross any branch cut and I'm on the first sheet, then it is guaranteed that the correlator is causal because all the branch cut and singularities, they are controlled by the light cones. But the non-trivial statement about causality, it's a statement on how, if I cross a branch cut, how the singularity can or cannot move. So the causality condition is basically this: if I cross a branch cut, this singularity is not allowed to move in this direction.
I'm sorry, I thought last time you said that if in the first arrow, that ensured that it's correctly time ordered.
You mean this one?
Yeah.
Yes.
So today you're saying that the correlator is causal. That's the same thing? I mean,
so time order, if you study time ordered correlator, you will not see any causality violation. So that's not the right 4-point function to study, because then all the singularities and everything, they are controlled by the light cones. So you have to cross a branch cut to see any problem. So that's like, so basically you have to study a correlator like this, where you cross the light cone of one operator and approaching the light cone of the other one.
Sorry, one question. There are, I suppose, an infinite number of branches in general, right?
For a single operator, or you're talking about endpoint function, or?
Just any. I'm thinking of a conformal field theory which has some sort of power law with a fractional power.
Yes. Okay.
So it's not like there are two branches that you can wind down the sheet many times. So this prescription that you cross the branch to get the other ordering, I'm wondering how unambiguous that is. What if I cross the branch twice?
We thought about that. There is no, like, I don't know if that's related to any physical correlator, but yeah, in principle you can do that.
I see.
And
it will be a solution to the Green's function.
Yes, but so what correlator that is, like, I have no idea. Okay. So today I'll show that at least in CFTs, this singularity on the second sheet, it will never move in the downward direction.
The statement that you cross the branch cut exactly once is a well-defined statement. What if I crossed from the other side?
You mean like doing something like this?
No. So to get to that same point, so if I did this, is that the same as crossing like this?
Yes, precisely. That's the same one.
Why is it the same?
So you can just think of this as basically you're just going here, doing like this, and going back, right? You did that one, right?
But I crossed from the other way.
Oh, I see. You did this one, right?
Yeah.
That is also one step.
Yeah, that's also one. So
Let me see what that thing is.
Yeah. It's like going to the, in one of them you are going to one higher sheet,
Mm-hmm.
and in the other one you are going to one.
Yes.
So for a square root branch cut, it doesn't make difference, make a difference. But for a cube, it would.
Mm-hmm.
So you have to give us a prescription,
Mm-hmm.
and then it becomes increasingly unnatural that one way corresponds to something, whereas the other way doesn't.
Yeah. So this prescription is fixed by the I epsilon prescription. So I'm just trying to think what correlator that will be. I think it's going to be a mix in the sense basically some linear combination of ordered and anti-time order, something like that. But yeah,
Did you look at the question that Loga asked last time? Some paper that claims that there were an infinite number of correlations?
not yet, but my guess is because this is a very simple, basically here I'm only analytically continuing one of them. So it's not going to be, there's no complication that can arise here. But if let's say I have two operators at time like separated and I'm analytically continuing both of them together, then you have to worry about like relative position of the branch curves, things like that. So then probably there can be some ambiguities, but I'm not sure.
Okay, thank you.
Before I proceed, let me fix some notations. So this is the 4-point function that I'll study. And so far this is a Euclidean correlator.
Sorry, for a 3-point function in a CFT, you could just do the analytic continuation and answer my question, right? Let's say I have 3 scalar operators. You
Then-
don't need explicit form.
Yeah, there is no like branch curve or
Why? There are fractional powers.
if there's fractional power there will be, yes, yeah.
In general, there are fractional
Yes,
powers.
yeah.
So there are all of So you could just go into any branch,
Mhm.
seems you just pick up some phase, right?
Mm-hmm.
So the question I was asking sounds almost like the anionic phases.
Even I think you can do that even in 2-point function, right?
You can do it in 2-point functions as well, yes.
Because you can just and but in 2-point function that will give you a phase and
Okay, we can talk.
and by using OPE you can write down the T-channel expansion. So by T-channel I mean I take this operator and expand around 1, and this is in the T-channel, this is given by some who are primaries and so these are conformal blocks. Let me, I'll use this cartoon for this sum. Similarly, you have S channel, which is this thing. where basically I'm expanding around 0, and you can also have U channel, which is basically you are expanding around infinity. Let me just not write that. But you have to be a little careful because it's not that all this sum they converge for all points. So you have to be worried about when you can actually trust the sum and when you cannot. The crossing symmetry.
So your
Yes.
operators O and psi are all spin 0 operators?
Yeah. So okay. Everything is scalar. Yes. And crossing is the statement. Is there a question?
And Z and Z bar are just a representation of the cross ratio.
Yes.
Although, I mean, they don't have the same, I mean, they look like two-dimensional homomorphic and anti-homomorphic, but it's just 1 minus Z
Yes.
is the first cross ratio and 1 minus Z bar is
Yeah.
the
Yes.
second cross
Yes.
ratio.
Yeah, because it's a CFT, you can just use this. Yep. So the crossing symmetry basically tells you that you can expand around. So basically, the S channel equals to T channel and equals to U channel whenever they converge. This might look like a trivial statement, but in recent years, people have used this to do a lot of nice things. For example, in Euclidean signature, if you can implement crossing in computers to eliminate different CFTs, and you can also do a lot of things analytically. One limit which is very interesting because you have analytic control is when two of the operators are almost null separated. They are space-like, but they are approaching the null limit. It's generally known by Light-Cone bootstrap, where yes.
So these Z's are what, please?
Real
complex.
So because they are complex, and because I'm working in the Euclidean signature now, the bar is just this.
What is Z, please? What I mean.
It's the basically cross ratios.
Okay. If you don't mind, could you define?
Okay. Yes. So far, you can just treat them as basically it's a.
It's just the location. Can I think
Yes.
it's just as the location of that point?
Yes. Yes. Yes.
So then, have you chosen that point to lie in a particular plane? 1-2 plane, for instance.
Yes. So
What
let
does
me.
1 mean? 1 means 1, 0, 0, 0, 0.
What? Okay. Let me just write it down. So generally, what happens if I have 4 separate points, I can just write it in terms of this correlator, where Z and Z bar is determined by the initial 4 points.
That's fine.
But now it's basically if my coordinates are.
Can I choose 1 to be 1, 0, 0, 0, 0?
It's here 1 is. It's basically that. It's basically 1.
And Z then is something that lies in the 1-2 plane, for instance?
1-2 plane, and it's basically Z is.
Z is equal to x1 plus I x2?
Yes, x1 plus I x2, and Z bar is.
Right. And so then on the Euclidean sheet, Z and Z bar complex. Right?
Yes. Yes.
Okay. And can you tell us what is the domain in which the 3 channels converge?
Yes. So
in terms of Z's?
T channel.
The 3 channels. What is the condition for under which S channel converges?
Let me write it down here.
Channel converges? I'd like to see how much overlap there is.
T channel it converges when it's 1 minus Z. Let me see. think that's correct. So this is for T channel. S channel is, and similarly for Z bar.
At the moment, I'm just thinking usually.
Okay. And this is for Z less than 1. And U channel is basically Z greater than 1. So S and U, they don't overlap at all.
Now, why? For instance, I'm not even understanding this. For instance, suppose I had. Oh yeah, I understand. And one that I thought the condition was that it's possible to enclose the 2 points in a circle, which excludes the other 2 points.
Yeah, it's possible, yeah. But if you write in terms of Z and Z bar, that's not possible.
No, but I thought that was the condition. Now suppose Z was to the left, so 1 is to the right. Suppose Z is to the left. Then no matter how big it is, it will be possible to enclose that point and 0 in one circle, which excludes 1 and infinity. So this sounds too restrictive to me.
S channel one, you mean this one?
Yes.
Let me see.
Do you understand what I'm saying? Shall I draw a diagram?
Let me just draw it.
We only care about the 1, 2 planes. Let's forget everything else. It's drawn on blackboard.
Okay, so my psi 0 is, let's say, here. 1, and so on is infinity. And so
Now I'm saying
What-
suppose I take my other insertion point to be far up there, further than 1.
So you mean the second one, right?
Yeah.
Okay. Let's see here.
Somewhere here.
Yes.
Now I can find a circle, a ball that encloses these two and excludes those,
Yes.
even if Z is greater than 1.
So basically, when you are expanding around some point, let's say here, right?
Whatever. And the condition for OP is that there exists a sphere.
Yes.
So I can do that even when Z is.
Yes. Yeah. Yeah.
So this sounds too restrictive.
So okay. Yeah. So basically, when I say S channel, basically that in that case, I'm thinking of expanding around 0. I don't have to, but if
Okay.
so, there is what you're saying. That's basically there is something called row expansion where people exactly do that. So basically they just go to some point where like somewhere here, let's say, and draw a circle. Basically,
Yeah.
so that's called row expansion.
Oh, but you want to expand around.
Yeah. Yes. Yeah. Yes.
Then it's clear. Thank you. But you may want to just increase the domain of overlap. You may want to do this kind of thing. Right?
Yeah. Actually, yes. That's technically that's what yeah, people do, and even in our paper that's what we had to do.
I see.
But like, so that's more technical, so that's why I didn't do it here.
Okay.
So you
Yes.
generally have one fixed for the other side of the expansion.
Sorry.
Here you are choosing always 0 to expand. There you are choosing 1 or infinity.
Yes. Yeah. Yeah.
Which one of the two?
So for T channel, it's basically around 1.
Okay.
For S channel, it's around 0.
No. Like here you have chosen like of the first two operator product expansion. You're saying that you'll always expand around 0.
Not always, depending on the channel.
Okay.
So I'm expanding around 0 when I'm in S channel.
Okay.
Okay. Let me now.
In U channel you have it around infinity.
Yes. Yeah. Okay. Now let me talk about Shockwave states.
That's right. Now these conditions were correct for Euclidean section. Now if you're going to analytically continue, what happens to these conditions? When can I cross the analytic continuum?
So that's a very good question. It's not always clear. So for example, when for certain cases the expansion has positive coefficients, only those cases it's clear that you can actually trust the Lorentzian signature expansion, but there is no like standard expression that I can write down.
So you're saying that outside the Euclidean sheet, the radius of convergence of your expansion is unchanged.
Yes, precisely.
So your analytic continuation is what Ix2 goes to x2. Is that?
Yes, yes.
This x1 x2 plane becomes, I mean,
X,
includes
X,
the time.
yes, yeah, yeah.
It's a reward coefficient for positive or negative causes problem.
So what might happen is this: in some channel you can write this expansion, let's say like star. So if this is positive, if you go second sheet means generally taking z and z bar around 0 or 1 or something like that. So if you take rotate it around 0, that will give you a phase. If this is positive, it's a positive sum, that can only decrease this whole thing. So in that case, it's well understood that it will converge, but it's not that you can always argue that this has to be a positive expansion.
So you're saying that if I move across the light cone in Lorentzian case,
Mm-hmm.
The analytic continuation is not always built in.
Analytic continuation can be well defined, but you may not trust these z expansions. You might have to go to row expansion or things like that. It's not clear that you can trust this expansion.
It's a question of the radius of convergence.
Yes, yeah.
It's not the analytic continuation may be okay with expansion.
By the way, if
Mhm.
your O and psi are all spin 0 objects,
Mm-hmm.
then this H bar will, I mean, the intermediate guy also will be a spin 0 object, right?
Not necessarily, no. No,
She's stressed in.
yeah, it can, yeah.
Sorry.
Sorry, one more.
Yes.
So the last in the last lecture you said that you will be comparing. You had some constraints for causality in between the first sheet and the second sheet.
Mhm.
So in actually computing those constraints, do you use this sum form or like you have some other expression to where?
Basically, I'll show that. Basically, I have to use this sum form in the sense just to argue that correlator is analytic in some region, and in certain limit, I'll mainly consider light cone limit. There, basically, you can actually trust first few terms of this series, and that will be useful. Yes. Okay, by Shockwave state, I mean this. Oh, I'm okay. Use this one. This is Lorentzian T. So basically, I'm inserting some operator at Lorentzian time 0, but Euclidean time delta, and I am working in the limit delta going to 0. So this Euclidean offset, it's basically it allows you to define a state with finite norm, and this is called a Shockwave state for the following reason. You can compute the stress tensor expectation value in the limit delta going to 0. You can show that it has support over only over an expanding null surface. So it's basically in the T y plane. It's basically something which is moving like this.
You do this calculation by computing the psi t o, the 3-point function,
Mhm.
and analytically continue it.
Yes, yeah. So, and the goal is basically to compute some correlator in this Shockwave state.
Can you just repeat why it is a shock?
So basically, if you compute this stress tensor, you can show that it has support only over some null, expanding null shell. So basically, that means it's just the stress tensor has support only here. Like everywhere else, it's 0. It's localized only here.
In this statement, there is no
No. And the energy of this state, it goes as 1 over delta. The thing that, yes.
You do this in the normalized state.
Yes, yes, yes.
So I'm thinking roughly the following, please tell me if that's
Mhm.
right. Then I've got my two operators, these two psi's, separated by this very small delta, and I've got a t.
Yes.
Then you could imagine the computation in the following way. You could first I'll just compute the norm of psi, norm of the state. That's
Yes.
essentially the 2-point function,
Yes.
which is diverging
Yes.
because these two guys are coming right here. Now, if I want the 3-point function, it's got a smaller divergence because the two psi's can't produce identity.
Yes.
It has to produce t.
Yes.
And that's why, unless this guy's very near, this thing goes to 0.
Yes. Yeah. Yeah.
And
Yeah.
then
Yeah.
Okay.
And because of that, exactly that case, phi you have 1 over delta. Okay. So this is.
It's not quite these functions.
Okay, so I'll consider things like this. So basically, I'll consider when this thing is 0, when it's non-zero, and causality says that. Okay, let me draw one more figure. This is my t. This is x, and the psi insertions they are here. So basically, it's a shockwave state, shockwave like this. One of the operator O is somewhere here at let's say x bar, and this is the light cone of that operator, and the other one is somewhere here. So this O is time-like separated with respect to size, but it's space-like separated with respect to the other O. So the commutator between these two, in this state, this should vanish because they are space-like separated. So that's the causality condition here.
These psi's and O's are different, in general different operators.
Yeah, they're in general different, but if you want, you can have like make them same.
But the two O's are the same.
Yes, yes, yes.
And the two, yeah.
Okay, so first I'll consider this correlator.
I'm sorry,
Yes.
I was spacing out. What your condition you said was that?
So basically, because this O is space-like separated with respect to this O,
Yes.
so this commutator should vanish in this state. Yes,
Yeah.
that's it. So let me consider this.
So the way that you've done this, it's just a special case of a 4-point function.
Yes, that's it. Yes, yeah. I could do everything with even without talking about the shockwave state, but it actually makes everything very very clear.
But it's a special limit of the 4-point function. When
Yes.
you take two of the operators very close to
Yes, yes. Because yeah, I can write down everything in terms of that g of zz bar, where this is at 0, zz bar 1, and infinity. But the condition then, I'll get the same condition, but it will be just little less clear.
It's effectively that instead of using 1, 0, infinity,
Mm-hmm.
you're using delta minus delta.
Yes. Yeah.
Just kind of manage.
The space part, which is 0 for the ket, does it become infinity for the bra or not? Or
Sorry.
why is it? What I'm saying is that you.
Oh,
have
this is
the-
yeah.
Yeah. No, what happens to that 0?
Oh, that's there. I'm just omitting, like it's there. I'm just not writing it. It's at 0. Special part.
It's also at 0.
Yes.
Thinking of the quantization along this line. Not
Oh,
really.
I'm always confusing.
So the what conformal invariance allows me, it allows me to write this as that correlator at 0, z bar 1 infinity with cross ratios z and z bar. They are first thing that I'd like to address. So this condition, what does it tell you about G of z bar?
No, sorry.
Yes.
Z and Z bar. Can you?
So this x bar, they are basically the light cone coordinates. I shouldn't write x here. Sorry.
Can one? Is this Z and Z bar also? Can we think of it as the position of an operator in the way that you've done before?
Yes. So exactly. That's why.
Which operator? Is it an O operator?
O operator. Yes.
And where is the other O?
Other O is at 1. That one, basically, this is psi 0, O z bar, O1, psi infinity.
Okay. So you can conformally map that to this
Yes.
with Z and Z
Yes.
bar.
Yes.
Fine.
So I can ask, like, what's the condition that implies causality, and so basically I want to derive some condition on this G.
And the condition that W and X were space-like separated translates into some condition on Z.
Yes. Yeah, it's basically that. Yeah, it's not a very interesting condition, but yeah, I can write it down.
The condition is probably obvious, right? That Z minus 1, imaginary part of Z is smaller than Z minus 1.
Yeah. So yes, precisely. Yes. Okay. When I write this G, okay. Let me now calculate that G. By calculate, I mean I'll start from the Euclidean correlator. So I want this correlator exactly in this order. So what analytic continuation I should do? From last lecture, you can just check this particular correlator. Let me just call it G hat to make sure that this is the Lorentzian correlator. This is basically take the Euclidean correlator, take Z to Z e to the power minus 2 pi I. That's the analytic continuation that will reproduce this ordering, Then just plug in this value of Z and Z bar.
Now I haven't understood. So what?
This is just so starting from the Euclidean one.
Yes.
So first of all, this is not a time ordered correlator.
Yes.
So this O is time ordered with respect to this is anti-time ordered with respect to this psi, but time ordered with respect to this psi.
So firstly, psi. When I say time order, I should be looking only at the Lorentzian part of the time.
Yes.
So both the psis are time ordered are spatially separated with respect to each other.
Yes.
So with respect to each other, we don't worry.
Yeah. So only this operator is important because this is time-like separated.
It's time-like separated both with respect to psi and with respect to the other. Right?
No. With respect to all this.
Space-like.
Yes.
I see. So both of them have to be after both the psis if they were time ordered.
Yes.
So the time order would be psi O.
Time ordered.
Psi on the right, O on the left.
Yes. Yeah.
Okay.
But I want this one. So basically, that's one analytic. Basically, the way I can compute this here, and then just analytically continue it to this point.
Now this I'm not understanding. If if you had computed it, I would have thought that you need to take both O's across.
No, this O is because it's this is space like with respect to psi. I don't.
It's space like with respect to psi. So only one of the O's.
Yes.
Okay, one of the O's is time like with respect to psi.
Mhm.
So you just have to take it across.
Yeah.
Across the branch cut corresponding to psi. Got it.
Okay. So let me just write it. So I take z to the minus 2 pi I z bar, and this just plug in z and z bar. So that will give me this correlator.
Wait, now you would have to take x across a cut. That's what I got from what you were saying.
X, yes, this x I mean. Yeah.
Now what this thing x across a cut? Why is that the same as doing this to z?
So what you can do just in Mathematica, you can just plug this z and z bar in and perform this analytic continuation. So you will just see that z goes around 0.
This should be obvious, right?
Yeah. So that's because like you can see just from this expression you can see. Yeah.
Fine.
Why x across the, you mean w across the cut?
Oh, W. Yes. Sorry. This one. Yes. Yeah. Okay. So now I know how to compute this. This 4-point function. Now the causality, this causality condition, let me just try it again, tells me that if I take this point very close to the light cone of the other O, there shouldn't be this singular light cone singularity that cannot move in this direction. Because if it does, that means this OO commutator that will become non-zero for even when they are space-like separated.
Just please say that again.
Okay. If I take this point and I take this correlator and I just try to approach this light cone.
Yes.
If because I'm crossing a branch cut, so that singularity may not be exactly at the light cone.
You're saying it has to shift up rather than.
Yeah, it can shift in the upward direction, but it shouldn't shift in the.
This is what you explained.
Yeah. Yes. So that's the condition. So so if that means the correlator in this region when I'm approaching here, the correlator should be analytic here. Otherwise, the OO commutator will be non-zero. From reflection positivity and crossing symmetry, you can actually prove that the correlator is analytic here. But it's a technical proof. I'll not go through the whole proof, but let me just give you the idea why it should be analytic, or consequently why the correlator is causal.
I'm sorry, what is that semicircle?
It's basically like this region, like I'm approaching this region, I'm approaching this light cone. So in this region, basically close to the light cone, there shouldn't be any singularity. That's all I'm saying.
You're approaching it along the like
No, it's just
any direction.
so yeah, I'm just approaching this light cone. There shouldn't be any singularity. I'm just that in this region, basically there shouldn't be any singularity.
And the lines that you're drawing are genuine singularities. They're not branch cuts, right?
Which
the
line?
Position, the lines, these 45-degree lines.
Yes,
that you
yeah,
draw Are singularities.
Yes.
They're the end points of branch cuts.
Yes, precisely.
Not branch cuts, not the branch.
No.
cuts.
That's the end. Yeah. Yes.
No, I just wanted to be clear. You can be going like slightly vertical in the opposite direction and meet the T line. And
Yeah, so
there
that's-
you would want it to.
So however I approach this light cone, there shouldn't be any singularity there.
What was your comment, Pranjal?
No, I just.
So you're saying why draw a little semicircle? Why not draw an entire strip?
Yeah, that's the cartoon. Like, that's just like I'm.
Yeah, that's. Yeah, I agree.
First, let me translate this in terms of a condition in Z and Z bar. If I define Z equals to 1 plus sigma and Z bar equals to 1 plus eta sigma, so you can map this region to something.
Wait.
Yes.
In Euclidean space, there
Hmm. Now they are not.
If you've got a Lorentzian space, what happens to Z and Z bar? Do they both become real?
No, they're still complex, but they are not a complex conjugate of each other.
Then what is the condition?
What condition?
There's no condition relating them?
No. So this is Z and Z bar.
It's a little odd, right? I mean, you had two pieces of data in Euclidean space.
Mm-hmm.
How do you multiply that amount of data? Are you telling me that now there are two complex numbers?
Now there are two complex numbers.
With obeying no conditions?
So yeah, so now two complex numbers, but that's basically because O and O, they have basically four coordinates.
You're saying that the Lorentzian correlator depends on more data than the Euclidean correlator?
That's not true.
Actually, he's not doing Lorentzian anything. He's doing mixed type of thing. You
No.
have both the Euclidean time system and the Lorentzian time system.
But still, no, it's a Lorentzian correlator. But even, the points, 2 points are Euclidean, but still it's a Lorentzian correlator.
But you're not switching off your Euclidean time components completely.
Except for delta, you are, right?
Yeah. Yes.
But like still, I think the way he's thinking is like in the complex time plane, he's moving around these singularities too. Is it not the case?
No.
Because only then will the Z and Z bar be completely independent of each other. Otherwise, even if you are completely in Lorentzian space,
Mm-hmm.
okay, then I mean like you still have only two independent coordinates. It's x plus it and x minus it.
In Lorentzian, it's not x plus it, x minus it. It's just x plus t, x minus t.
Oh, sorry, x plus t and x minus.
Then you would have expected Z and Z bar to become real. That's why I was thinking.
Yeah.
But it's not real because exactly, yeah, that I delta, it's
Because
not.
of delta.
Yeah, yes.
But in the limit, the delta goes to 0, it
Mhm.
will become real.
It will be 1 plus I delta times something, yes.
Fine.
Yeah. So basically, yeah, in the limit delta going to 0, basically sigma goes to 0. That's the statement.
Delta goes to 0, sigma goes to... Oh, so Z becomes 1.
Yeah, Z and sigma is imaginary.
Sigma, and what about eta?
Eta is basically the ratio, like how fast I'm approaching this light cone.
Is eta real or imaginary?
Real, okay, yeah. Eta is greater than 0, 1, and sigma is imaginary. It's very complex. So, and this statement, just because you can find out sigma from here, you can just map that statement that the singularity shouldn't appear anywhere here. That's basically the complex sigma plane. That's basically this condition. So in the upper half plane, near the sigma equals to 0 point, G should be analytic here. Don't take this semicircle that seriously. It's basically in the neighborhood of sigma equals to 0 and imaginary sigma greater than 0. The correlator should be analytic. So that's the.
Sorry, where did that come from?
It's basically just from here. You can just find out sigma. So that's this sigma is basically this region. It's basically like I can just write down sigma. It's basically it says that if there is a singularity here, there will be a singularity here.
So the imaginary direction in sigma is basically measuring how close your operator is approaching the right one.
Yes. So imaginary part of sigma is basically this region.
So then again, the semicircle is not a thing you can.
Yeah, it's basically all I'm saying is in the neighborhood of sigma equals to 0, it's analytic. Okay, so the I don't need this part.
So sigma is equal to 0 when it touches the vector.
Yes, yeah. Okay, so the proof that the G this G is actually analytic here.
Wait,
Yes.
did you say that again? And which parameter parameterizes how near you are to the light?
So sigma is basically sigma equals to 0 is basically this point.
And what about delta equals 0? That's what?
That's also sigma going to 0. That's sigma. So sigma has basically sigma is proportional to something like this. It's 2I delta 1 x bar or w bar minus 1 over x, something like that.
eta parameterizes what?
Eta is roughly, I can be wrong, just let me write some expression. It's basically
some angle between them.
Yeah, let me give you a better description. So you're basically far away from the other light cone, I guess. So you have this light cone. You're far away from this one, but you're approaching the other one. Something like that, probably.
So suppose sigma was small.
Mm-hmm.
So I'm approaching this light cone. Eta tells me where I approach the light cone.
Yes, yes.
Okay, fine.
So it's you're basically far away from this point. This point.
So it's a coordinate along the light cone line.
Mm-hmm.
When sigma is small.
And it's the most important parameter in the sense that in the light cone bootstrap, this is the smallest parameter in the theory in the computation, and that's very, very important. Okay, so the proof has two parts. First of all, crossing symmetry tells me that I can generally, when one operator approaches the light cone of the other operator, it's generally easier to expand around the other operator and work in that channel, which is basically in our case a T channel. But crossing symmetry tells me that I can expand it around any other channel. So if I expand around this channel, which is the T channel, just from reflection positivity, you can actually show that this quantity G, sigma eta, just from T channel expansion, you can show that this G is analytic in this region.
I'm not understanding what channel are you bringing the two sides together?
No, that's one psi, one O.
One side, one.
Yes.
Okay.
So that's not the very natural channel.
Should have been S, no?
In my notation, that's S. Sorry, yes, that's S channel. Yes, yes, that's yeah. So in the S channel, you can actually show that this thing is analytic. So that means this G hat is analytic and this correlate is causal. This is a very important point, that this G hat is analytic in this region.
About what point are you doing the expansion?
About 0.
How does that work? How do you manage to? You can't make a sphere around 0 that.
He's already placed one of the size at infinity.
Yes, yes.
Not in this diagram.
But he's also talking in terms of Z and Z bar. Actually, sigma and eta parameterizing Z and Z bar. So essentially, his comments are in the other diagram where one is at 0.
Yeah. So basically, when so I'm writing it here. It's basically this. Okay. I have, so this G is basically psi 0 O Z bar. Here I'm expanding around this psi.
So you're saying the question of whether you can enclose something by a sphere is not conformally invalid.
Yeah. Yes. Yes.
I didn't even know. So this is a bit odd. You're saying the criterion for when an OP is valid depends on which conformal frame you're in.
It's OP is still valid, but I cannot trust the sum. So it depends.
When an OP converges.
Yeah.
You're saying the criterion for when an OP converges depends on which conformal frame you're in? How can that be? I thought this was conformally, all terms of conformally invariant.
No, but I can just move around the points and then convergence will change, right?
But you're not saying that you're moving. See, in this diagram.
This is a wrong way of saying it, yes. But I'm expanding actually in
I understand, but what worries me is that you're reaching two different conclusions from two different conformal frames.
Not really. So you can actually forget about this diagram. I can just talk about everything in terms of Z and Z bar.
No, but now suppose I wanted to go back to
Okay.
Sorry,
Yes.
let me
Yes. Yeah.
just to make sure I totally understand. In this diagram, it seems that you if you apply the criterion you explained to to ask?
Mhm.
Which means you cannot expand around 0
Mhm.
or expand around any one of those psi points.
Mhm.
Or maybe now that because you're going to, I actually I don't even.
Oh, it's in the Euclidean. There is
Yeah,
this.
it's this Euclidean Lorentzian.
Uh-huh.
But anyway, please, just to understand,
Mhm.
how do I know? In this diagram, it looks like I shouldn't be able to expand around 0 because.
If it's exactly at 0, I would agree.
No, let me separate them. I won't be able to expand around any one of these because any sphere you draw will that's of reasonable size will have the other one inside.
But like that, the other one will be even in the complex direction. So I'm not. I don't think. I think that will matter because this Euclidean shift, but I don't have a good reason why.
So, because the time-like separator psi and rho, okay, even if you take the sphere of size I delta by 2, the distance between psi and rho is less than delta by 2, right?
Sorry, can you repeat that again?
I mean, the point is this, that psi and rho are time-like separated.
Mm-hmm.
Suppose you take a thing started at one of the size which has a radius delta by 2.
Mm-hmm.
Okay. Point is O still inside the sphere because the distance between psi and rho is negative.
I see what you're saying.
I mean,
Mm-hmm.
I don't know if this is the correct prescription, but you can imagine like because Lorentzian there are also some prescription that we got.
I see what you're saying. You're saying, for instance, had it been on the light cone, it would have been nearer to O than to the other side. Because, I mean, that psi had O been on the light cone of the top side,
Mm-hmm.
psi and O would have been the nearest operators in the game,
Mm-hmm.
even though the other sides look like that.
Yes. So, probably I should have said that I'm expanding around this light control, I guess.
No, but even then, these psi's are local insertions.
Mm-hmm.
They are both inserted at 0,
Mm-hmm.
and except for a small Euclidean separation, one is at plus I delta, the other one is minus I delta.
Mm-hmm.
So what kind of, I mean, these psi's are always close. However much you bring O and psi close together in terms of null distance.
But the distance between these two is del square, like something like that. But I can always keep it somewhere here.
Good, you do that.
Uh-huh.
But
So that distance can be smaller. Like delta is not the smallest parameter.
no, but the distance between psi and psi
Mm-hmm.
is infinitesimal. I mean, it's what can win that?
No, basically this is the smallest parameter of the theory. Delta is not. So like I take eta goes to 0. I'll take eta goes to 0 first. Then let's say I'll take delta goes to 0.
And when eta goes to 0, where does
Let me just.
Well, you hold delta fixed and
Eta goes to 0 should be.
It should be on this.
But I'm not even sure if this expression is correct or not. But still. So this is my. C bar 1. It looks like it should be somewhere on the light cone of this one. I don't even think this expression is correct. Let me check if I have.
It should be opposite.
Hmm?
Bar thing should be little bit down
Yeah.
and unbarred above with a sign, overall sign.
There should be an overall sign minus.
so what is the game that you are holding delta fixed so that the two sides
Mm-hmm.
are a finite distance away,
Mm-hmm.
and you are bringing O to 0 null distance
Yes.
from one of the sides.
is that what you're doing?
Not really. This eta doesn't tell you anything about the distance between these two light cones, this light cone and this.
Ronald's suggestion was that it works because because even if it's finite, it's a negative distance. And negative is smaller than 2. But since you haven't given us a criteria, is that what you're? Suppose just for a moment.
Yeah.
Suppose you took both your O's and put them onto the at Lorentzian time equals 0. So we were doing everything Euclidean.
Lorentzian equals to 0. Okay.
Lorentzian time equals 0. Then would this OPA have been valid or not? Because that picture seems to suggest it would have been. Unless Z becomes large. I can't see all this. I just want to understand whether firstly what we're looking at is a Lorentzian effect or not.
Let me just think for a second. Yeah, I agree. If I write down in terms of Z and Z bar, then I don't even see, like, I'll say that it will converge as long as Z and Z bar is smaller than 1.
Right. And can you convert that diagram with both O's Euclidean into this with Z and Z bar less than 1 by a conformal transformation? Sounds suspicious because what you're saying is you're changing which are the nearest two operators in the product. In the original frame, clearly it was not possible. Sure, a conformal transformation should change that, right? Or not?
Basically, it might be what you said in the beginning. A conformal transformation can basically change the point around which I'm expanding.
This worries me because I thought that the OP was a conformally invariant. So what you're saying is that the criterion for when an OP is valid is not invariant under conformal transformations. That should not be right.
One answer, there is one thing that you can do. You can do that row expansion that basically it's
that you can. But let's not let's stick to just to understand exactly the firstly I have a conjecture. The conjecture is that if you take this with everything Euclidean and transform to that, I can't do this in my head, but you will always get Z and Z bar larger than 1. I just wanted to know whether you thought that was a reasonable conjecture.
That might be possible. It's not. Yeah, that might be possible.
Okay. Then next conjecture is, however, if you do it Lorentzian, you can do it by getting these things reasonable value, and then the interpretation will be what Ronan said, which is that this is somehow negative. Is this what's going on or not?
I'm not 100% certain, but because in the row expansion, it's not. It doesn't even show up. So probably.
Yeah, row expansion, I can see that you can enclose both those in a circle.
So that there it doesn't show up. So I think.
But are you going to do the row expansion or are you going to expand around?
Technically, that's what we did, but here I'm not showing that.
Now in the row expansion, even if this was a Euclidean plane, it would be okay, right? Because I can always find a circle.
Yes.
That just skims this.
Yeah.
You can do that.
Yes. So that's what we did in the paper, but yeah, it's too much for to do it here.
But then but then you're not expanding around the point of insertion. So it's not like the Z is being. Doesn't sound like you're phasing the Z.
But then what you get, you can just final answer. You can just write down in terms of sigma and eta.
Okay, so you do. Okay.
Okay, now I have to use. I can use this fact that G is analytic in this region to derive some constraints.
So just what was what are we doing here? We're doing the OP around which point?
So we are in this language. We are just doing just to conclude that this is analytic. We have to do this OP
around the point of insertion of psi.
In the row expansion, that's not correct. But yeah, in principle, around some point where basically this converges.
Around some point where that converges. Fine.
Yeah.
That sounds good. Okay. And how are you going to conclude that it's analytic? You're going to explain. I
can give you the brief sketch. It's basically it comes from reflection positivity.
Yeah, just at least roughly, just
okay.
What goes into it.
Okay. So let me just do it for the real line, so it's very easy.
But just to ask again,
Huh?
now it's if you're doing this row expansion, then this analytic continuation is it still z goes to e to the power 2 pi I z?
Yeah, it's something similar to that. Yes.
Something similar or that?
The analytic continuation is this, but at the end I have to write down everything in terms of rho.
Okay. Yes.
Sorry, I missed what rho was. I mean, what was rho?
So rho is basically some like
The center of the circle.
yes, some way of expanding everything in terms of some other point where. Let me just explain why. Let me just take a point somewhere here and explain why it should like OP should converge here, because this is the easiest one to do. So on the first sheet, though I'm writing ZZ bar, it's basically everything comes from the row expansion. This has this structure.
Now, sorry, just to understand, it was sort of important for you to do psi O, so you will get positivity. Is this the point?
Mm-hmm.
Is this the point?
Basically, in that channel, because of that, I can say that they're
It's a
positive.
perfect square.
Yes, it's positive.
Is your main point that if you take a bunch of perfect squares and then you change each bunch of positive numbers, then you change the phase,
Mhm.
that becomes smaller?
Yes. That's yeah. Do you want me to go to?
I think you should say, but I think I understand.
Yeah. So this has this structure. Just from reflection positivity, you can show that they are positive.
And for this, it's very important that you did psi O, psi O.
Exactly.
You did O, psi, psi.
Yeah, then it's not true. Yes, precisely. That's why in this channel, you can actually conclude that it converges and it's analytic. So now if I, let's say at this point, Z and Z bar, they are positive. So now if I take this and do this analytic continuation, that will give us since this is positive, this is positive, this is positive, a phase only can decrease the norm. So what you can say is the following. This is bounded, this is G hat because it's on the second sheet. It's bounded by the first sheet.
So firstly, you've demonstrated that this is within the radius of convergence of the OP.
Mm-hmm.
Yeah, because that's the first thing you will have to do.
Yes.
That you can use the OP.
Uh-huh.
And you're saying that, well, if it converged without the phase, then it clearly converges with the phase.
Yes. Yeah.
That's the first statement.
Yeah.
Secondly, the convergent answer is going to give us something that's not infinite.
Yes, precisely. Yeah. So that's why it's analytic in this region. Yes.
Is it exactly the reflection positivity setup because you need the points to be the size to be at mirror points of each other,
Mhm.
right?
You can map this into that.
Only then will the A's be positive.
Yes. No, A's are independent of the points.
But
The-
won't you get crossed out unless you have this exact mirror thing?
So you have to, but what you can do, you can arrange it in a reflection positive setting. Then you can conclude that H bar is positive.
Yeah.
This doesn't depend on where your points are.
Oh,
If you conclude that they're positive, they're positive.
I see. So you're using some analysis.
You know, you know, if you wanted to do this, the most natural thing to do would be to do radial quantization.
Yeah.
But radial but if you do this radial quantization business, you can write a conformal transformation mapper to cylinder, which is S3. Okay, and then you use reflection positivity on that cylinder. So now you've got S3 and you've got time going on. So let's say there's 0 time. Then you put some insertions here, insertions there. That would be the standard radial quantization thing. But then that would imply the positivity of those edges. because now you're doing an OP. So it's just a normal square.
Yeah, no, I was just worried about if it's not mirrorly placed, you might get some C1, C2 instead of C1 squared everywhere.
Yeah, but you see, as you were saying, these A's are just properties of the expansion.
Yeah.
So what you can figure out what the positivity of the A is from any experiment and then use it.
Okay, now let me just derive some constraints. Okay. So this quantity G hat.
Okay, so now we've completed the proof of causality.
Yes. So yeah, and now I'll use the fact that this is analytic in this region to derive some constraints. So this is G hat of eta and sigma. Okay, let me make some comments that will be useful later. So generally, when people talk about light cone bootstrap, in terms of eta and sigma, that's basically eta going to 0, keeping sigma fixed.
Can you draw that on a diagram? This makes no sense to me even. I mean, what does it mean physically?
In terms of cross ratios, I can tell you, but physically, it's basically. Oh, I can. Okay, yeah. Let me draw one diagram that might be useful. Let's say I have two operators. Let's O, and two other operators. Let's say psi. So this this limit means, and basically whatever I'll do here, it's basically the reflection of this operator. Yep. So what this light cone limit is basically, I'm approaching this light cone. Yes. Then basically I'm just approaching this light cone, keeping this distance fixed. That's the light cone limit.
So we have operators separated only in one spatial direction and only in real time.
Yes. And
This is now we're not talking about this shockwave state anymore.
No, it's just a general statement.
A general statement. Okay.
So this is the light cone limit. Generally, the interesting limit is first this, then taking sigma to 0, which is basically first you approach this light cone, then take it to infinity. So that's the light cone limit this is the limit that will basically.
And can you? I know people use this light cone limit a lot, but sorry. I'm going to put this phone off. Intuition for why is this limit particularly interesting? What is special about it? Something like that. I know people use it a lot. Why is this so useful?
It's useful in the sense that you can actually do analytic computations because because in the limit eta going to 0, the only thing that matters in the T-channel expansion is the operator with lowest twist.
Yeah, can you explain why?
Yeah, so yeah. So just before that, there is one more limit which is important.
And T-channel means what? Which two are you bringing together?
Basically these two. And there is one more limit which is important, which is called Regge limit, which is basically keep eta fixed and sigma to 0. And in this diagram, that's basically, if my O is here, I'm approaching this light cone and infinity at the same rate. Okay. But for today, I'll just stick to light cone limit. Okay, so why light cone limit is important? So in this limit, you can show that the correlator in S channel, or in terms of eta and sigma. So now I'm normalizing everything so that I have the identity exchange is 1 plus some operator m times plus dot dot dot. So what you can show that in this limit, the leading contribution after 1, the leading contribution comes from the term with the lowest twist.
Now, can you explain why?
Just if you like write down the confound block.
Some intuition.
Let me.
Why? I mean, this is just pulled out of a hat.
Let me.
I've heard the statement 20 times,
Mhm.
but I'd like to know, have a way to think about it.
Let me see. You're saying why, like?
Why not lowest dimension, for instance? Why? Where did the angular momentum enter? I mean, usually operator product expansions are suppressed by dimension. I know there are free indices, so presumably you're contracting those free indices by the small distance. But just if you could explain roughly what. Say again about this Lycon limit, if you can draw your diagram.
Mm-hmm. That okay.
And keep that, if you don't mind, keep the diagram on the board.
Let me draw it here then. It's basically this limit.
And the limit that these guys are going towards the light cone, that you said was controlled by which one? By eta.
By eta, yes.
And
yes.
then sigma is how far it goes.
Yes, yeah.
So then operators with lower twist are suppressed by higher powers of which one? Eta or sigma?
Eta.
So it doesn't matter. Sigma could be finite.
Yeah, it doesn't matter. Yeah, yes.
Okay. So naively you would think that these operators are coming very near to each other because the light cone distance is very small.
Yeah.
So naively you would think that terms with the lowest dimension in the OP would contribute. Because, and for scalars that would be right, according to your formula, right? Because if you've got O1, O2 and you've got some O3, then you get the contribution has increasing powers of delta x depending on the dimension of that O3. So naively that's what you would expect. So its lowest dimension would be very reasonable. But you're telling me it's lowest twist. Now, suppose O1 and O2 are scalars. The thing that thing has, the new operator has a dimension, means that there are also x's to contract the indices.
What do you mean x's?
If you don't mind.
Yeah.
So suppose I have OX1, OX2, and I'm doing some V mu1 to mu L. Okay. By we have some x1 minus x2 to some power, and then we have to contract these indices.
Yes, precisely.
And first, is this right that these indices have to be contracted with x1 minus x2?
Yes. Yeah. If you have spinning operator over here, you can also contract with them with that.
What?
If you have like spinning operator, like if you have less stress tensor, you can contract that with.
I thought this was the operator.
Oh, this is your V is okay. Yes, yeah, and or you can have derivatives and things like that.
Right, but let's ignore descendants for a moment. I
Okay.
just want the contribution for V, not its descendant.
Okay.
Then this is the only structure? Okay. So now if that's the case, this will go like I would have thought. Suppose this was delta, let's be simple, these go both delta and this is some delta prime and A prime. Then what we would have expected is that we need to compensate. So we would need 2 delta minus delta prime plus L prime.
Yes.
L prime is same as L prime.
L prime is L. Is this the point, that this delta prime minus L prime combination appearing? Is that basically what's happening?
Yes, basically this is yeah. So if you have descendants, yeah, it will be probably more complicated. You'll have derivatives and stuff. But basically, yeah, this is how we get delta minus L. I can give you a better proof next day.
But is this more or less the
Yeah, basically this is kind of proof that I'll give you on.
And just to be totally clear, in Euclidean space, this would not have helped. Because in Euclidean space, if x1 minus x2 is small, then x1 minus x2 mu is also small.
Yes, yeah.
So the net power of x1 minus x2 would just have been controlled by delta. However, in Lorentzian space, we have this funny situation where we can make x1 minus x2 norm small without having the individual get small.
Yeah.
And that's why the singularity is controlled not by the dimension, but the twist. Is this right?
Yes, yeah, and
so it's a purely Lorentzian thing. That things being controlled by twist happens when you come near the line code for this very simple reason. That's very interesting.
yeah. So actually, yeah, in the Euclidean signature, you get the lowest dimension operator. Yes, that's correct. Yeah,
Seems obvious.
yeah, but and that's why there is one more thing actually. Even okay, because we're talking about.
But just before we continue, I just wanted. I'm giving a rough intuitive proposal. I'm not at all sure of it. I just want your assurance that this is roughly correct.
This is roughly correct. I'll give you another proof, which is basically this one.
Okay.
So that's.
It doesn't sound right to me.
No.
So in like in two-dimensional CFT, you know, so it would be like Z1 minus Z2 to some H of the intermediate guy. So let's say, you know, you have whatever it is, O1, O2, and there's some OP. So it would be something like this, and Z1 bar minus Z2 bar, HP bar. HP bar. Now I think his notation, this is just 1 minus Z. And this is 1 minus Z bar. Correct. And whatever comes upstairs, that's mod, mod 2 power something. Okay. And I have some operator in the middle, P, which has spin. Now this object he calls sigma, H, P, and this object he calls eta, sigma, H bar, P bar. So the eta dependence does pick up only H, P bar. So what I'm saying is that this.
Could you do your expansion around the z equals 0 if you don't mind? Oh, you want me in this?
Well, I just wanted to map to what he has here. I can do that.
Wait,
that would be Z, H, Z bar, H bar. And basically, I'm saying that this could be thought of as, I mean, I can, yeah. And is this something like this, H minus H bar?
And that's basically eta, the second one.
Yeah, this is what you were calling eta.
Yes.
And what the H and H bar? H and H bar with the
H and H bar are the
dimensions of the
conformal
produced
and holomorphic and anti-holomorphic dimensions of the intermediate operator.
of the operator you're producing.
Yeah. Yeah. So this is H bar. So what I'm saying is that no, maybe I'm not disagreeing with what you say, but I'm saying that it is possible to pick up by looking at only dependence on this object. It is possible to pick up H minus H bar. And if I set up some.
But like
But
you
I
can.
don't know why it dominates.
Why? Yeah.
And z goes to 0. If you were in Euclidean space, the thing
So yeah,
that
suppose z goes to 0 in such a way that z bar also.
but in Euclidean space, z and z bar are the same.
Yes.
Are the same. So,
So the h minus h bar is irrelevant.
So basically,
Only depends on h plus h.
So I'm just agreeing with you. Yes.
But you have to be in a situation where
Yeah, I have to do something else in which z saved over, yeah, I don't know. Yeah, okay. I'm agree with you. Yes.
Okay.
So
Yes.
you can like construct certain limits in which you actually approach the other operator, which would be like the Euclidean limit. In a sense, you approach both the light cones together, and in that case, it will start depending on the dimension again.
Yeah, that's what's called double light cone limit. Basically, yes. I think so.
Is it useful in certain
It
scenarios?
it is useful, but like you have less analytic control, but you can you can say few things about the theory by considering that limit.
You can say only as much as what you can say from Euclid. Is that the case?
As much that I'm not sure, but yeah, that's a very useful limit, but I guess it's not as easy as the light cone one. Okay, so this function, this is well known in any dimension, and for yes.
Does mod z have, if mod z, the way you wrote it, cross ratio should be 1, right? So it's constraint sigma. So line on a circle. Sigma equal to -1.
Say that again.
If mod z 1.
Mod z, yeah, okay,
It's 1, right?
yes.
Constraint the sigma to lie on a circle around -1.
So if you think of that Shockwave computation, yes, but I'm talking about like I didn't even have to talk about that Shockwave 4-point function. It's a condition on G of ZZ bar that like so that Shockwave kinematic that's basically shows it very clearly that why it has to be true, but that's just an example of this. Okay, so now what I can do, I can compute this in the limit eta goes to 0 first, then sigma goes to 0. So this goes as 1 minus some I times lambda so this lambda is basically proportional to COOM COO size. Few comments. First of all, because you are going into the second sheet, there is an enhancement of 1 over sigma.
Your first.
That's the first sheet.
Statement. What is the G? G have to say.
So that's called light cone conformal block. It is known in any dimension. It is some 2f1 basically.
And it can be thought of as the contributions of descendants of that operator.
Yes.
But presumably all descendants or only special descendants contribute?
All descendants, yes.
But in this particular light cone limit,
Yes.
all descendants contribute?
Yes.
Okay. It's not like okay, fine.
Probably some derivative, like it's.
I was wondering exactly that. Do only the derivatives along the light cone
Yes,
derivatives?
all descendants, but only with those derivatives, yes. But not like anything with in this diagram. Basically, you cannot have derivative with respect to this coordinate. Only the coordinate which runs this way. Yes.
Okay, so some special. So that's why it's simpler.
Yeah.
Because only special descendants.
Yes. Yes. Yes.
It's almost like a two-dimensional or something.
It's basically You can compute this from two dimensions. Yes.
I see. Fine. And please go on. Okay, so you've got some explicit expression there. Fine. Then what's the next statement?
So it's basically I'm going to the second sheet, then taking this limit. Like this is basically for any sigma.
Okay.
But I'm interested in eta going to 0, then sigma goes to 0 limit.
Yes.
So that's in that limit, it's basically this expression.
Why are we interested in sigma goes to 0 at all?
So it's basically when you are approaching the light cone.
I thought eta goes to 0 is approaching. Sorry, did I get that wrong?
So basically this is let me.
On those arrows, just say what is sigma, what is eta. What do you do if I want to approach the light cone at a finite position? Which do I take to 0?
So there is not an exact map, but more or less, if this is my v coordinate, this is my u coordinate, it's basically,
Those arrows, what do I do to approach the light?
so yeah, that's what I'm just writing down the position of this operator O. So the u coordinate of that is basically 1 over sigma, and v coordinate is basically eta times sigma.
So v going to 0 is approaching the light cone,
And then,
and I want to do it at fixed u.
yes,
So I hold sigma fixed and take eta to 0.
yeah, then I'll take both of them to infinity.
Why do you want to take both of them to infinity? I thought the question of causality was you could address even.
So that the reason is basically the condition that I derived here, the analytic condition, that's basically close to sigma goes to 0 limit. So I have like, I can write down an expression, but I don't have any condition on that expression.
Wait, but I thought you wanted to ensure causality everywhere. Now you're only ensuring causality very far up.
Yes, yeah. So
So that seems like you're imposing too little.
yeah, it's too little. Yeah, that I agree. But that should be sufficient for us in the light cone limit. Yes.
You're saying it's some condition, but it may not be the most general.
No, not at all. No.
Okay.
For example, like that singularity that can actually appear far away from the light cone. It's not like that condition we didn't even consider.
Okay, so you just because for technical reasons you're considering the limit eta goes to 0 first, and then also taking the limit sigma goes to 0.
Yes, yeah.
Okay.
And one just comment, why like this sigma going to 0 limit is actually at times important. So in this limit basically you can write down this light cone OP in a very nice form. It's basically the integral of stress tensor.
This I haven't yet understood also. Why is sigma going to 0 simplifying it?
It's probably I can do everything for finite sigma, but I don't know if I can prove that the correlator is analytic for any sigma.
Yeah, but just it's a more general question than exactly your thing. In the whole light cone program, why does sigma go to it?
No, in the whole light cone program, actually, it's not the only limit that people talk about. No.
But is it a specially simplifying limit?
It's basically, for example, when people talk about anomalous dimension, this is not even the limit that they talk about.
What limit do they talk
So
about?
it's, as far as I remember, it's basically probably sigma goes to 1, I think.
Why is sigma going to anything particular specially simplifying?
Okay.
Explain that eta going to 0 brings 2 points almost null. Therefore, OP should be very good. You know, that already sounds simplifying.
Yes.
What is the additional simplifying by taking sigma to some simplification from taking sigma to some special value?
Is that the one which allows the high twist operators to dominate? Or?
Just sigma goes to 0. Which limit? This limit actually.
He's already told us that eta, taking eta small, gives you domination from low twist.
Yes. Yeah.
So then why
Low twist.
Yeah. And why does
So
taking sigma to anything special help anything? I'm sorry, it's just a question of deep ignorance. But just because I hear so many talks taking on these funny limits, I just want to get that straight.
one thing basically.
Sigma, if you take eta to 0, sigma has to go to 0 automatically.
Why?
From that, those expressions that you give.
Eta and sigma, they are independent of each other.
Mod of that bar. That should become 1.
Why? I didn't even understand this. Why is z bar?
No, it doesn't have to be 1. No, there is no reason.
That expression you are taking. Suppose eta goes to 0, then mod of that bar is 1.
Why does mod of z bar?
Because z bar is 1 plus eta sigma. If eta goes to 0, z bar is 1.
It's exactly 0, yeah. But that doesn't. Yeah.
Sigma will also go to 0 if you look at z.
But z and z bar, they are not related.
Mod. No, see, z is like t plus x, z bar is like t minus x. You can just do whatever you want. That complex one?
No. One reason I can tell you why people talk about sigma equals to 1. It's basically technically what happens. There is a
Where does sigma goes to 1 in that diagram?
in this diagram. It's like it's not even clear. Like why you even think about sigma equals to 1.
Okay.
So it's basically in the light cone the standard light cone bootstrap. where basically people talk about sigma equals to 1, that's because there is some branch cut at sigma equals to 1.
But if there's a branch cut, I should be able to see a physical reason.
There is now I'm trying to avoid that because they use some others. Their sigma is little different from this sigma, so
So actually, I don't even care what which special value of sigma, but just I want to know what special physical
Okay.
phenomenon happens. At
yeah,
per-
let me
per
let me
value of sigma.
let me draw this. That will be so. Let me draw. So there is an operator 0, z bar, 1, and infinity.
I'm sorry to.
No, it's
not your own work. Just because I think you know enough to explain something that I've never understood.
So when I should draw a bigger diagram. Zero, 1. So this is z and z bar. So one limit that people talk about is basically when z and z bar both goes to 0. When the ratio, this is generally how they define given sigma. So basically you're approaching one light cone first. It's something like this. You're approaching this light cone first, then you're approaching this one. That's the standard light cone bootstrap. So that's why you have some branch cut and there is a log, and that basically gives you enormous dimension.
Okay, I'll try. Thank you.
So people generally use different convention for z and z bar, so it's kind of confusing. Okay, so because of this enhancement, let me make one more comment. So all the causality constraint, they are basically for 4-point function which has this particular form. It is actually small but growing. Whenever you have this kind of term, you can expect that there can be some condition on the numerical thing that appeared.
You got that sigma to the power ln minus 1 from the known form of this g tilde?
Yes.
Okay.
And one more thing, for spin 1, there is no enhancement, but for higher spin, like for spin 2, you have a 1 over sigma term, so there is an enhancement, so you can expect that you can constrain that term. So let me just show you briefly how this can be useful. So let me just take g hat.
I'm just sorry.
Yes.
So I can think, but at sigma goes to 0, is taking what on the diagram is doing what?
So in this diagram, you're taking this point to be at first it approaches this one, then you take it to infinity.
And can you explain just intuitively why that limit has an enhancement?
It's not. One, it's basically it is picking up some residue. So what is going on basically at this 4-point function, you can think of you're doing some contour integral over this line. So if it's at finite distance, so basically you have to take into account the contour which basically the semicircle that's at infinity. Not at basically this integral over here. On the complex plane, it's basically something like this. So if there are some poles, you have to take the consider them, and also the contribution that comes from.
It's great, but it's very technical. I mean, isn't there a simple physical thing to say?
There is, but let me see.
I'm sorry, you should just go on. I'm asking unfair questions.
There is, but all of them I have to at least go to some technical details.
Wait, in the picture that I had on the board,
Uh-huh.
I expand OO,
Uh-huh.
I get these X's.
Uh-huh. So from there you can see it clearly.
This is what I wanted.
Okay, yeah, from there.
I think I know what you're going to say. You're going to say that the things in the numerator become larger. Is this right?
Things in the numerator, precisely, yes, yeah. And I can actually tell you exactly how they can go.
So there are the V exchanges,
Mhm.
and then the V exchange is multiplied by differences of X's in the numerator. And those are becoming larger and larger as you take sigma.
Yes,
And then in full block, you get powers of this.
yes,
That enhances that.
yes, but yeah, precisely. It goes as like V times U square, something like that, and that's basically 1 over sigma.
Fine, thank you. Okay.
One question.
Yes.
Is your psi placed at infinity or some finite point as you're drawing in that diagram?
This diagram?
Yes.
Which one? These two?
Yeah, those are psi insertions.
Yeah, so they can be anywhere.
Finite.
Yeah, finite.
Finite.
Yeah.
So I thought that when you're writing the 4-point function, you had
That's and this picture, they are different, not the same picture. So it's
okay, because I was worrying like when you're at the 4-point function that you're using is actually with a psi at infinity, right? So is it related to approaching the light cone of that particular?
no, this is a different picture. So that's why like don't it's confusing. This picture has nothing to do with whatever I was saying before.
And actually, my thing about the diagrams actually explains the power of sigma.
Uh-huh.
Because there were L differences.
Yes.
I don't know why the minus one is there.
Minus 1 is basically because even your V has sigma.
Probably that, right?
Yeah.
So, but otherwise, the L differences of that gives.
So you're getting the maximum contribution for from the highest spinning operator.
No, because I'm taking eta to 0 first.
Yes.
So it's basically the lowest twist operator.
Yes.
So then basically, if you have, yes, and that's actually important. And okay, let me now do this. Take this g hat because it's analytic. I can just perform this contour integral over this.
So that would basically be the operators with spin same as the dimension of the operator, because twist cannot go negative again.
Twist,
Twist cannot also be 0.
yeah, twist basically it's restricted by the dimension of space-time.
So it's in 3 dimensions, twist is greater than equal to 1, except
So if I just take this g hat, perform this contour integral, because it's analytic, so this thing is 0. So I can.
What are you doing here?
So basically, I'm just doing this contour integral. So
You're integrating what?
this g hat.
Okay.
So a line and this. The radius is r, and r is much greater than eta, but much smaller than 1.
You're doing this with a complex sigma plane and
Yes.
fixed eta.
Fixed eta, yes. And r is basically small but larger than eta. So what you can do along this line, you can just use this light cone expression because that's for finite sigma small eta.
Good.
But along this line, you cannot do that because, for example, here sigma is smaller than eta.
Yes.
So what you can do, you can just perform the circular integral. You can write down this pi lambda eta. That's the contribution from the semicircle.
Yes.
Equals to minus r to r dx or d sigma.
Wait, now why did the contribution from the semicircle, what happened to that sigma to the power whatever the denominator?
Okay. So now I'm just focusing on I'm just doing a special case where it's the stress tensor. L is 2 and tau is d. But I don't have it can be it's just the simplest one.
Yeah.
So this is g hat eta at sigma. It's in any day. It doesn't matter.
What about the power of eta?
Okay. Oh, I guess that should be there.
Were you in 4 dimensions?
Yeah, let me just put it in 4 dimensions, I guess.
Yeah.
But it doesn't matter. I can do it in any dimension.
I understand, but the formula you've written this for.
Yes. So I can just probably write this down, this power.
Yeah.
Now again, what you go, as I said earlier, so the second sheet.
And why is it? Oh, you G minus. Thank you. Yeah, go ahead.
So first of all, this expression, this relates. This left-hand side, this is a IR quantity because it's just the light quantity with the smallest twist operator.
Yes.
But the right-hand side, it basically this integral which has everything. This is the UV contribution. So this is basically something that relates IR to UV.
Beautiful.
The second thing is just from, as I argued earlier, on this real line, the second sheet value of G hat is bounded by the first sheet value,
Yes.
which is basically 1.
Yes.
So that means this is greater than or equal to 0 because this quantity is positive.
Yeah.
So that tells me that lambda has to be positive. So that's the causality condition.
Lambda was what now?
So lambda is basically whatever that appears here.
And
And in
includes the.
it's basically for stress tensor is just COOT, C psi psi t. But I know you might say that that's like this is too much of a work to derive that this is positive, because just from what identity this is positive. This goes as delta O delta psi.
Yeah.
Over. Yeah. But what you can do, you can actually derive more constraint. So this is one way of deriving this lambda greater than 0 constraint. You can use maximum modulus principle, which says basically the value of G hat, the magnitude of G hat is inside this disk is bounded by its maximum on the boundary.
Just before you go on, to summarize what you said on the outside we can use the OP,
Mm-hmm.
and that gives you this lambda.
Yes.
On the inside, you can use
Reflection positivity, yes, basically.
reflection positivity to argue that this is some particular sign.
Yes.
And therefore, that because the whole thing is 0, you find that lambda as a
Mm-hmm. So I can derive the same thing using maximum modulus principle. Let me just give you the results because it's not anything technically challenging. And I guess everybody.
Why was it 1 on the Euclidean sheet?
Okay, that's basically because I just normalized everything with respect to like my G's are on the first sheet. It is basically I define it as psi OO, psi over.
I suppose I'm asking why would it have a particular sign on the Euclidean sheet?
On this sheet.
Yes.
So that's basically that comes from the reflection positivity. So it's on the second sheet this value is bounded by the first sheet value, and first sheet value is basically 1. Okay. So now let me just list all the results. For scalar external operators.
Because you chose your configuration such that you could draw a line.
Mm-hmm.
I just want to understand how
Mhm.
reflection positivity was being applied there.
It's basically that same argument that I gave. It's basically that that coefficients are positive, and I'm just giving it a face. That argument.
But here you're using that the whole Green's function is positive. Right? You're saying the whole Green's function is positive there.
Mm-hmm.
And you can see that probably directly from reflection positivity.
Yes.
Because you've chosen a configuration which is reflection.
But there is one technical problem. So I cannot use the S channel expansion here. I can just go to the U channel one.
No, but that's what I was wondering. I was wondering whether you could just use the abstract expression for the Green's function.
Mm-hmm.
Without any, for that you don't want to use any other. I thought you didn't want to use an expansion.
No, or like I can trust the expansion. Like at least I can trust the S channel expansion here.
Okay, but not near the,
Not near.
the origin.
Not even near the. It's S channel expansion that's valid over this half. But I have U channel which I can use over here.
But can you just show the positivity of this without doing any expansion?
Probably yes, but we don't have it. Yeah, probably yes.
Okay.
Because next lecture, basically, I don't even have to go to the other channel. I can do everything in the T channel. So that's
Fine, okay.
so now consider the most general case. So I have multiple lowest twist operators with various spins.
What are we trying to do now?
So basically, I'll just list all the results. So if all the external operators are scalars, but the exchange operator, it can be any lowest twist operator with various spins. What we show is the following. The spin 1 conserved current, there is no constraint. Simply because the factor that comes in the light current bootstrap is basically 1 over sigma to the power L minus 1. So there is no enhancement for spin 1, so there is no constraint. For L equals 2, it's basically this greater than 0, which is actually obvious. But what you can also do, just from maximum modulus principle, is you can just check it that if all the higher spin conserved current are excluded. What that means is the following: you cannot have finite number of higher spin conserved currents. If you have one, you have to have an infinite number of them. So that's basically what Maldacena and Zabieda proved in D equals to 3, and there is some generalization in higher dimension. It's basically the same condition.
Not any other one of them is excluded.
Like any finite number of them is excluded. If you have one of them, like you cannot have finite number of higher spin conserved currents.
But you prove that you need infinite number of things.
You cannot prove it. It's basically individually each term is basically excluded. But you can have an infinite series. You can sum them, and it can be something which is well behaved.
Yeah,
That's
if you've got a finite number, then it's the one with the largest angular momentum as Prandtl said that dominates, right?
yeah, but you can exclude that. Then you can exclude the one before that. So basically, you can exclude all of them.
Right.
So, but you can just sum them up and
So if you cannot, you show that there cannot be a largest angular momentum.
yes, basically, yeah, precisely. Yes.
And what was the nature of it? Was the same algebra that you had there?
It's basically what you can show is that maximum modulus principle says that the magnitude should be maximum over this boundary.
Okay.
So if you have basically let's say spin L equals to 4,
Yeah.
what you can show that basically there is some region like it doesn't matter what spin it is as long as L greater than 2, there will be a point where the magnitude will be larger than it's on the boundary. You can just plot in Mathematica. You can show.
Where does that come from? The same algebra?
From the contour integral, you cannot show that. Probably you can by choosing some complicated contour, but from here it's actually very easy.
Can you just very roughly? I haven't understood. Actually, maximum modulus principle is just that if you have an analytic function, it reaches its maximum is on the boundary.
Yes, yeah.
Okay, and how are you
Okay.
using that?
Okay. Let me do it here. Let me do it for the spin 2 case then first. For spin 2, I know it's bounded here by 1 on the real axis, and here I have that light current expression. I know what's its value here. Then I can just, let's say I'm moving along the imaginary axis. If I just decrease sigma, I can just compute the magnitude. From that, I can just find out the sign of lambda, because it shouldn't. From here, it shouldn't grow.
How do you know that because everywhere on the boundary
Yes.
it's the same. I see. Great.
So now, if I have spin,
That comment I didn't answer.
so yes.
Yeah.
So because the magnitude cannot increase inside, because it's bounded by 1 here, and I know its value over here.
And that's larger than
Yes. I don't initially I don't know if it's larger than 1 because I don't know the sign of lambda. Let's see.
modulus larger than.
Yeah. So if I move this direction, it cannot increase from here. So that is basically that's why the terms that's growing in sigma, there is a constraint. And what you can show that if I have spin higher than 2, it doesn't matter like basically you can consider this region, like you can basically what you can do, you can just go in this direction, you can exclude one sign, you can go in this direction, you can exclude the other sign.
This is because of the phase of sigma.
Yes, yeah. So that's why I said like I can probably do it from that contour integral, but probably I have to choose something like this.
I see. So the way I'm understanding this is that if you've got a 1 over sigma cube, then you can go here and change the sign, and then go like that.
Yes.
Fine.
Now for operators with spin,
If we want lunch, we better stop in 5 minutes. Gautam anyway is leaving, so.
Okay. Let me just then, let me just say this. Let me just write down the constraint. So in CFT, this JJT 3-point function, where J is spin on conserved current, T is stress tensor. It has a known structure, but you can write it in this form. Some structure. So this is basically what, these are known structures and these two are numbers. So basically the structure is fixed by conformal invariance, so up to 2 numerical factors. Similarly, the stress tensor 3-point function, it has 3 structures. You don't have to know what these structures, what they are. All you have to know that there are 3 numbers which come from the theory. So if you give me a theory, they'll have some particular value. If I do the same thing that I did for the scalar case, only the computations will be a lot messier.
You get inequalities for all.
Yes. So what we found is the following. So this, for any CFT, this should be true. We actually derived a part of these constraints. Then people who are experts in light-cone bootstrap, they derived the rest of them. So what we derived, this is from causality. Then I don't remember before us or after us. So Komargotsky, Zobiedov, Kulaksizi, Parnachev, they derived this from deep inelastic scattering. But the important thing is Hoffman and Maldacena derived this in 2008 using averaged null energy condition. So they assumed average null energy condition. From there, they derived these conditions. So that made us wonder if we can derive average null energy condition from causality. And the answer is yes, and that's what I'll talk about on my next talk. So let me stop here. Questions?